This is the second PowerPoint associated with spectra from stars. This discussion of spectra doesn't have to be limited to stars, but we're mostly going to focus on stars eventually. When scientists analyze the spectrum that comes from a light bulb, a star, whatever is giving off light, I already talked about how they do that using a diffraction grating. If they just analyze a single element, as you see in this picture, there's a hydrogen spectrum, a sodium spectrum, a helium spectrum. If they just analyze a single element, for example in the lab room, they can isolate elements in a container and then excite that container with electricity so that the gas inside the container starts to glow. And they've learned that each element gives off a unique combination of colors. You might remember from chemistry class learning about how electrons jump energy levels in an atom. And when they get excited, they jump up to higher energy levels, and when they de-excite or release that energy, they fall back down. And when they fall back to the lower level, they release their energy in the form of a light wave. And different atoms have electrons that do different kinds of jumps, and the spacing of the jumps is different, so different colors are created when those jumps happen. And so each atom is unique. Each atom has its unique spectrum, or sometimes we call it an atomic fingerprint. Each atom has a unique fingerprint that tells you when that atom is present. So by studying individual elements on Earth, we can identify what fingerprint each atom has. Astronomers can use that when they're analyzing spectra to try to figure out what chemicals are in the substance they're looking at. Real spectra are usually combinations of these things. So for example, a light bulb, a fluorescent light bulb, might have some combination of the patterns you see here, all combined into one image. And that means there's multiple gases in that light bulb that are contributing to give you this pattern. When astronomers do it, they sometimes are looking at stars, sometimes they're looking at nebulas, sometimes they're looking at the atmospheres of other planets. This is the kind of thing that helps us figure out what the atmosphere of Venus or the atmosphere of Titan looks like, or what Jupiter and Saturn and Neptune and Uranus are made of. We can figure out the chemical compositions of these gases by analyzing spectra. So to further get deeper into it, I want to show you the types of spectra. There are going to be 3 types, and for each type, you're going to need to be able to answer these 4 questions. So you could set up a little table, perhaps, where you know you're going to answer these questions for each one. What is the spectrum called? What does it look like? What conditions are necessary to make this type of spectrum? And can we name some specific examples of actual objects that do produce this kind of spectrum? I'll walk through each of the spectra and hit all those things. You might choose to pause the video at times, either to capture a picture into your notes or to write down some words, because some of these answers get pretty elaborate. So here we go. The first type of spectrum that objects can create. Oh, here are all 3 of them shown together, but you don't have to write them down yet. I'm going to take you through each one. So let's take a look at the first one, called a continuous spectrum. So first, you're supposed to know what it's called. I'm telling you that it's called a continuous spectrum. What does it look like? Well, it looks like all the colors. You see it right here. The entire rainbow of colors, Roy G. Biv, they're all there. There's nothing missing. That's a continuous spectrum. What causes this kind of spectrum? A continuous spectrum is created by an extremely hot substance that has electrons that can move about freely. So that's your key sentence. Again, maybe you want to pause to get that piece of information. A continuous spectrum is created by extremely hot substances that have electrons that can move about freely. Now, I hope by now we've already covered the fact that electrons, when they move around in certain ways, they create electromagnetic waves. I'm doing one of your wave dances now. They create electromagnetic waves. And so this is saying the electrons in your substance can move freely, which means electrons are moving in all different ways. And if electrons are moving in many different ways, they're going to create many different colors. This electron over here is creating blue, and this electron over here is creating red, and all the colors are coming out. So you see the entire spectrum of light, Roy G. Biv, it's all there. Some specific examples. The fourth question is, where are some specific examples where this can happen? So here are a couple of specific places where this happens. The first one is a traditional filament light bulb. That's the old-fashioned bulbs that are starting to get phased out. They have an actual wire in the bulb, and that wire, when that kind of light bulb burns out, you can hear that wire rattling because the wire has broken. And what happens in those light bulbs is they run electricity through the wire, and the wire gets so hot it just starts to glow. But because it's a metal wire, one of the things that's unique about electrons in metals is a lot of the electrons in a metal are free to move around. Not all of them, but a lot of them. So if the electrons are free to move around, that meets one of our criteria. And when we run electricity through, it starts to get really hot. That's the other criteria. So now we have a hot substance with electrons that are free to move around, and it creates all the colors. So a traditional light bulb, also called an incandescent light bulb, makes this pattern. The other place where we would see this pattern is the lower part of a star's photosphere. Now, if you haven't already done the work taking notes on layers of the sun, you don't quite know what the photosphere is right now. So you might want to go do that work, but if you don't, for now, this photosphere is one of the layers of the sun, and that's where the light of the sun comes from. That's where the word photo comes from. Photo means light. And so that part of a star is actually made of charged particles that are flying around. We call that plasma. And charged particles are moving freely, so we got that. And of course, stars are crazy hot, so we've got a hot substance with electrons that move about freely. Just to clarify, this is a lower part of the photosphere, so that part makes a continuous spectrum, but the star as a whole, by the time the light gets out of the star, it's not going to look like a continuous spectrum anymore. It's going to look like something else, which we'll get to in a moment. That's spectrum number one. You got to know what it's called, what does it look like, what causes it, and some specific examples of where you could find that. So make sure you've got that in your notes. And here we go. The second spectrum we're talking about is called an emission spectrum. An emission spectrum is created by a hot substance that has electrons that are not free to move around. They can move, but only in specific ways. The electrons are stuck inside their atoms, and electrons and atoms can jump energy levels, but they can only move in very restricted ways. So for example, let's say I'm dealing with hydrogen, because I think this pattern might be hydrogen. If I'm dealing with hydrogen, electrons in a hydrogen atom can do very specific jumps, and those jumps allow the electrons to make only these colors. So hydrogen might make these particular colors and only these colors. Helium, electrons in a helium atom would make different colors. So these electrons do move, but they're not free to move around any way they want. They can only move in specific ways, and therefore they will only produce specific colors. Some specific examples of where this would happen would be a fluorescent bulb. A fluorescent bulb is filled with some gas, and we excite the gas using electricity. The electrons jump up energy levels, and when the electrons settle back down, they emit the color of whatever jump they're doing. If they're doing a big jump, they might release blue. If they're doing a small jump, they might emit red. Maybe we'll talk more about that later. So depending on what gases you put in the light bulb, that will determine which colors you're going to get. Another example where you find this is, it says our gas tubes, but I do plan to show this to you in class, but I'm not sure you've seen it yet. So if we haven't seen it before you're doing this PowerPoint, know that I'm going to show you some gas tubes in class that do create this kind of spectrum. And finally, some nebulas create this kind of spectrum. A nebula is just a giant collection of gas in space, right? And if the nebula is hot enough, sometimes there's a star in the nebula that heats the nebula. If the nebula is hot enough, then the nebula will glow and it will emit light. It will produce light on its own just because it's hot. But again, since it's made of gas where the electrons are attached to their atoms, it's going to only produce specific colors of light, whatever those electrons are allowed to do. Hot as the inside of a star. So in the previous spectrum, I was saying inside the star, it's so freaking hot that the electrons are actually not attached to their atoms. The electrons are actually free, and again, we call that plasma. And so those electrons are moving independently of their nuclei. They are not tied to these jumps. That's the continuous spectrum, where electrons can do anything. In this spectrum, electrons are restricted. They can only make, this is a nucleus, these are electrons, they can only make certain jumps in the atom, and therefore they can only make certain colors. That's spectrum number 2. The third spectrum is called an absorption spectrum. And I want you to look at this picture, and then I want you to I'm going to go back a moment. I want you to compare, in this picture, the emission spectrum and the absorption spectrum. And I want you to notice that those two spectra have exactly the same pattern. It's just that in one case, it's basically dark with certain bright colors. And by the way, the emission spectrum really should just be black everywhere else. I don't know where I took this picture from, but it shouldn't look gray. It shouldn't look dotted in those other places. It really just visualize that's basically black between the bright spots. In the absorption spectrum, it's the opposite. All the colors are there except a few. Just some colors are missing. And notice it's the same colors that I had in the previous one. Whatever chemical is making the emission spectrum in the middle here, the same chemical would make the absorption spectrum, but it does it under different conditions. It's the same pattern, so it's the same chemical, but it's under different conditions. So let's see what those conditions are. For an absorption spectrum, this is created by, you have to start with a continuous spectrum. So if a continuous spectrum of light from some hot source then passes through a colder substance, the colder substance can absorb some of the light, but the colder substance will only absorb certain colors. So we say it selectively absorbs. It will only absorb certain colors because the electrons can only make certain jumps. When electrons jump up energy levels, that's when they absorb energy. And so if the gas is cold, the electrons are kind of sitting at low energy levels, and they can get excited by the light that comes through, and they will absorb some of that light, and then that light doesn't come through, and you don't see it. Really, the best example of how this happens is stars. We said a couple slides ago that the lower part of the photosphere produces a continuous spectrum. It produces all the colors. But then that light has to pass through the outer part of the sun, which is a little bit colder. So as the light passes through the outer part of the sun, the colder gases near the outside start to absorb certain colors, and those colors never make it out of the sun. So when we look at a star, we actually see an absorption spectrum because the outer layer of the photosphere actually removes or absorbs some of the colors that were produced down below. This is probably the hardest idea, so you make sure you keep track if you have questions here. And I'm going to talk about it a couple more ways, but this is definitely the hardest spectrum.